Hey everyone, in this video I will work with historical time series dataset of Bitcoin prices taken from actual market on each minute basis and apply 4 algorithms on it, which are ARIMAX, FB Profit, Xgboost and also Lstm, and check the performance or evaluate those models on their ability to predict the prices in future. And obviously the code for there is an entire notebook will be in my GitHub, and also I will put a link of the dataset that I'm using for these historical prices of Bitcoin in a Google Drive. I'll share the link in the description. And the data for Bitcoin price is quite long in this case, that is starting from 2012 up to 2021, but obviously you can download this data using various API, free API I mean. For example, Y-Finance has a very popular Python package with which you can download the historical prices of any ticker, including Bitcoin or any other cryptocurrencies. But once again, the data for this video I will share as a Google Drive link in the description of this video. Now, one of the key points here is using different models or algorithms to be applied on the same data to see what kind of prediction or what kind of evaluation metrics I'm getting. Now, the key point is about the model selection, that is what kind of models or which model you should select to be applied on a time series data for any asset prices, for example. And in this regard, just few things to mention here is that there are some indicative properties of your data to figure out in your EDA exercise, that is when you are exploring your data, which can guide your model selection. And normally stationary time series are good to tackle with ARIMA or Facebook Profit. Then time series with seasonality and trends can be tackled by Profit in a good way. ARIMA, although offering support for seasonal and non-stationary time series, often underperforms on the seasonal or non-stationary time series versus Profit or Lstm. And finally, Lstm it's a deep learning model, obviously, and Lstm can be applied to any sort of time series problem because it requires, only thing is that it requires a lot of data and also your time to train will be definitely longer because the more layers or the more network you add to your Lstm. And further, whenever your time series is highly unstationary, you may find it useful to try to tackle your problem as a classical machine learning regression problem. But overall, finally, in summary, you will almost always have benefit from training multiple models and then comparing their performance, which is, in my opinion, definitely the best result. That is, on the same data set, apply as many models as possible and then check or evaluate the performance. And for this exercise here, you need to install few of the extra packages unless you have them installed already, and they are the PMD ARIMA, then FB Profit. Now, while installing FB Profit locally with my Python interpreter of 3.8 or, for example, 3.9, I saw that I was getting some errors. So after doing some Stack Overflow research, I found that you have to also install these package with this particular version 2.14. So you have to run these PyStan as well before FB Profit. All right, otherwise the other packages are just the regular ones. I'm using Pandas, NumPy, Datetime, Seaborn for my plotting, ITER tools, and later I'll be also importing the TensorFlow packages before implementing the Lstm part. I already have downloaded the dataset in my local machine. You may want to keep it in your Google Drive while using it in Colab, or also if you are familiar with the SageMaker Studio Lab from AWS, then you can use. So I was trying this particular notebook in both Colab and also in SageMaker, and that's why here in this cell I have a different source directory for the dataset. But here for this video, I'm going to use the local machine's downloaded dataset. So here is my dataset. And when I do a btcdf.head, this is what you get. So this is the original dataset as it is. And so what we have here is the first column is timestamp, then the regular OHLC numbers, that is open, high, low, close. Then I have volume in BTC, volume currency, and finally the weighted price. Now note that I have many NaN values here, which we are going to deal with in a second. But let's see some other things about the dataset. So here I'm just doing btcdf.info, and what do I get? I get 0 to, so these are the total number of entries. We have quite a large number of rows. So I have 4 million 8, so I think it's 4 million 8 857,376. That many number of rows I have. Yeah, so this is good enough data set to apply your deep learning model, because here I'm going to use LSTM at the end. Yeah, so that's some introduction to the data. Now, first thing I'm going to do is converting the timestamp column from string to date time. Um, for X in BTCTF, let's wrap it in a from timestamp X for X in, yeah. A lot of rows, so it's taking a few seconds. Now run it. Yeah, so now my this timestamp is converted to datetime format. Compare this with the previous. Here it was just Unicode numbers. Okay, now let's check the shape. Yeah, 4,857,377, and I have 8 columns. And now I am going to use pandas setIndex method on the timestamp. Now, why it is necessary is because by default an index is created for any data frame, just like we see 0, 1, 2, 3, 4, all these index are automatically created by pandas. But you can set a specific column of a data frame as index if required. And like a dict, that is a dictionary, a data frame's index is backed by a hash table. Looking up rows based on index values is like looking up dict values based on a key. In contrast, the values in a column are like values in a list. So looking up rows, when you're looking up rows in the with the index values, is much faster than looking up rows based on column values. So having the index is only advantageous when you have many lookup of this type to perform. In our case, we are going to do some lookup, and that's the reason I'm setting setIndex with timestamp. And sometimes the index plays a role in reshaping the data frame as well. Many functions such as setIndex, stack, unstack, pivot table, melt, cross tab, etc., all use or manipulate the index. So overall, the main benefit of having an index in your data frame is that it will give you the ability to do your lookup in a more time efficient manner. Timestamp. I have a column name called weighted price. So here I'm plotting that. So I need to define a fixed size. Let's do 16 by 10. And here is a plot. So our data starts around in 2012 January, and for a very long time the prices was almost closer to the zero axis, and then from sometime around 2017 18 it started really moving fast all the way towards the sky. All right, now I need to handle the missing values in these time series data. For that, the first step is to detect the count or percentage of missing values in every column of the dataset. This will give an idea about the distribution of missing values. So let's check for that. So here I'll be dealing with the missing values in the time series data. Let's quickly see what does it. Okay. All right. Let's figure the output. So missing percentage will be yep 0. I'm going to concat these two missing values and missing percentage across the axis of 1. Yeah, so by default they are assigning the 0 and 1 into the head. So what I can do for this is, let's see, columns equal to 0 would be values and 1 would be missing percentages. Oops, I'm still getting what yeah, so I need to provide in place. Okay. All right, next step is to do some imputation. Because my data has a lot of NaN values we saw earlier. So I need to do something about them. And what I'm going to do is imputations. And the reason that I'm going to use linear interpolation is because it's time series data, and time series data has a lot of variations against time. Hence, imputing using backward fill or forward fill is not the very optimal approach. Rather, the better alternative is linear interpolation. So linear interpolation simply means to estimate a missing value by connecting dots in a straight line in increasing order or decreasing order. In short, it estimates the unknown value in the same increasing order from the previous value or decreasing order. And this image that you see right here is taken from the Wikipedia. You can just directly search for the Wikipedia's linear interpolation page. What it gives the mathematical representation here, and it explains it very well. What it says is, if two known points are given by the coordinates x0, y0, that is, this point is x0, y0, and another point is x1, y1, the linear interpolant is the straight line between these points. For a value x in the interval of x0, x1, that is, x0 is my here and x1 is here. For a value x in the interval x0, x1, the value y along the straight line is given from the equation of slope. So the equation of slope is y minus y0 divided by x minus x0, which will be equal to y1 minus y0 divided by x1 minus x0, which can be derived geometrically from the figure on the right. It is a special case of polynomial interpolation with n equal to 1. Solving this equation for y, which is an unknown value at x, gives me the linear interpolation. So to implement the imputation with linear interpolation, I am going to use a little util function, fill missing, that will take df. I'm going to go column by column. So what are the columns we have? Let me see. I have open, high, low, close, weighted price, volume. Okay, let's do them all. Open. And this interpolate method is coming from pandas. You can check their documentation for the proper definitions and the options that interpolate method will take. Close. I pretty much just need to change these column names. That is all. So on the next one, open, close, I need high and low as well. That will be, and I need volume and weighted price. And lastly, I can just print df.head from here. Also print df is now just to check if anything is left. Okay, and run this cell. BTC df. Okay, it was executed relatively fast, and we can see that these are now, I cannot see any nan values, and when I print this is null, that also does not give me anything. Okay, so that means everything has been properly taken care of with imputation. Next, before proceeding further, I just want to create this timestamp as my, I'm going to just apply set index with the timestamp. So BTC time. Yeah, so now currently my index is referring to the timestamp column. Now, very basic, some basic EDA just to see the distribution of the data. So my first one is to just plot with AXB span method. We will see what this is. So weighted price big size equal to set X label and set Y label. So this AXB span method, it adds a vertical span or a vertical rectangle across the axis. The rectangle spans from x minimum to x maximum horizontally, and by default takes a whole y-axis. So I need to provide x mean and x max. So my x mean will be 2018/12/01, that date, and max is color equal to red, 0.3. Similarly, I need to do x AXH span, that is horizontal span, which is kind of the vice versa thing of AXB span. AXH. Here I'm going to use 17500 because it's a price. Color, and let's put the color equal to green. So H span will take the entire horizontal, and for the vertical it will take between these two values as a minimum and a maximum range. Alpha remains same. 3. And this is a plot I get. So this is my V span between these two dates, and this line, green line, is my H span, which is between these two price points. So well, let's also plot Kde plot. So this kernel density estimate is used for visualizing the probability density of a continuous variable. It's used to see where the mass of the data is located, and I'm going to use this I'm going to plot this KDE on weighted price, and we can imagine that most for a very long period, that is almost for 60% of the data, the price was really very low. Only from 2017 onwards and probably 2018 onwards it's going up. So we can see that trend in my KDE plot. Weighted price, it's going to take a little bit of more time because our data is kind of large. Okay, so we can see, as we expected, that the density is most towards a 0. That's obvious because there is a downward trend if we take a long-term view of the BTC price. Okay, now next I'm going to do a lag plot. So lag plot are used to observe the autocorrelation. They are crucial when we try to correct the trend and stationarity, and we have to use a smoothing function. So lag plot helps us to understand the data better in this kind of circumstances. For time series, lag plot is really important. So plt.figure. pd.plotting. Weighted price, that's my time series. And then first plot just lag equal to 1. That is, I'm plotting here 1 minute lag plot. Dot. Let's just do this first and see the result. Where single argument to subplot must be a 3-digit integer, not lag plots. Let me correct that one. And it's actually sub sup super title. Yeah, now it should work. Let's see. I'm plotting with a 1 minute plot. Yep. So the one that's my 1 minute lag plot. And now I need to do this for my hourly lag, daily lag, weekly lag, and also monthly lag. It will be just kind of the same. I just need to change um, this index here. So the next one will be 332, the third one will be 333, and so on. And the lag also will be changing. So for the hourly, it will be 60, and daily, it will be 1440, like this. So let's do that. Yep, that's my code. It took a couple of minutes to run, and this is my lag plot for hourly, daily, weekly, and monthly log. And what we can see from this is that we can see that there is a positive correlation for minute, hour, and daily lag plots, but we observe absolutely no correlation or very, very low correlation for monthly and weekly lag plots. So it makes sense to resample our data almost at the kind of daily level, thereby preserving the autocorrelation in that way. So in the next step, that's what I'm going to do. That is resampling, time resampling my data. So basically, the idea in resampling is that examining stock prices or any asset prices, for that matter, stock price data for every single day or every single minute, which is the case here, is not of much use for practical purposes. That is for investment decision by financial institutions who are more interested in spotting the market trends. So to make it easier, we use a process called time resampling to aggregate data into a defined time period, such as by month or by quarter or even by hourly. So institution can then see an overview of the stock price trend and make decisions according to these trends. And for this, I am going to use Pandas resample method. So this Pandas library has a resample function which resamples such time series data. The resample method here is similar to the Pandas group by method, as it is essentially grouping according to a certain time span. And let's do that then. But before converting to hourly resampling, let's quickly go back to the original data frame that we currently have and see the timestamp here. So here we can see it's a each minute data. So I have 1322, 1323, 24, 25. So each of the rows represent one single minute. And that now I'm going to convert to each hour. That is, I'm going to resample this data frame on an hourly basis. Resample. Reset index. Run this cell. Cool. Now this has converted to hourly data. So we can see that 13, 14, 15, 16. So now this is each hourly data. So to summarize what just happened above is that the data.resample, that is my data frame.resample, this line right here is used to resample the stock data, that is a Bitcoin price data in this case. The 1H here stands for hourly frequency and denotes the offset values by which you want to resample the data. And the mean indicates that we want the average stock price during this period. So for this entire 1 hour, we have 60 individual data points for each minute, and we take the mean of it, and that becomes the data point for our hourly for that particular hour. Yeah. So now I am going to do some more plotting, but now I'm going to use a Plotly library because that's kind of interactive. Let's see if it will be properly presented in VS Code. Oh, but before plotting that, this one was on an hourly basis, but like I said, I really wanted to convert it to on a daily basis. So price daily would be BTCDF. Yes, now it's on a daily basis. So I have the dates changed 12, then 01, 02, 31, 01, 02, 03, 04. Yeah, so now it's on a daily basis. And now I'm going to use a plotly to plot some graphs here. So I need to import reset index. Sorry, this is TRUA. So in this interactive plot, I will be able to select 1 month, 6 month, 1 year, and 2 year as a slider or span. And that's why, okay, so that was px.line, and next I need to do fig dot over mode is x. And now finally the actual configuration of the map, which is update x. range range selector. That is where I'll be able to select, and it takes a date, and buttons equal to list, and that list will have again another date. First is 1 month of slider. Backward. Change it to 6. Next one, 1 year. To year. Lastly, date step equal to all. And you can check out their official documentation here for that range slider plot. So this is an example in their documentation, range slider and selector in Python. Now you can implement range slider and selector in Plotly graph purely with Python. So it takes data frame, then you add this fig.update layout, and that's where you pass x-axis as a dict, and that will take range selector, that will be another dict, then buttons list, and there you pass all the individual span of ranges, and lastly dict.step_all. This is exactly what I followed in here as well, and the map should be like this. You should be able to select like this. Okay, let's go back to my code here. Syntax error, invalid syntax. Let me fix this. Yeah, there is a syntax error indeed. And what is that? Let me fix. Yeah, obviously between all these dict I missed the comma. Run it again. Cool. Now that's my beautiful interactive plotly representation of my time series data. 1 month, 6 month, this is 1 year, this is 2 year, and this is all starting from 2012 all the way up to 2021. Right. Okay, this looks good. And now I'm also going to do a candlestick graph. So plot. And I'm going to select 2, 0, 1, 8, 12. Go.candlestick. Am I choosing the right one? Anyway, yeah, I think so. Candlestick. X will be my plot. Oops, sorry. Plot index. That would be my open price. Next high. That would be high. next low. Yeah, let me fix that. This is my plot data. Now run it again. Again, plot. Oh, yeah, I have to run it and then. Cool. So that's my candlestick plot on the data with 2018 December. Okay, that was some of the basic idea. Now I'm going to do time series decomposition and a statistical test. Very important, and you always got to do with any time series project. Okay, and for that I need a lot of imports from stats model. That's a package I'm going to use for all my time series calculation. And these are the imports: seasonal decompose, Kpss, add fuller. This is required for checking the stationarity. And I'm also going to plot these autocorrelation function. For that, I'm importing plot ACF and plot PACF. Okay, now first, let me make sure that no missing values before you perform all this test. So for missing values, we already built a fill missing method. To that, I just pass the BTC price daily, this data frame, run it. Cool. Let me check if there is any missing values. No, all are yeah, all are imputed. Okay. But before going further, a quick word on these seasonal decompose coming from statsmodel.tsa.seasonal. So the stats model library provides an implementation of the naive or classical decomposition method in a function called seasonal decompose. It requires that you specify whether the model is additive or multiplicative, which we are going to do in a second. So both additive or multiplicative will produce a result, and you must be careful to be critical when interpreting the result. A review of the plot of the time series and some summary statistics can often be a good start point to get an idea of whether your time series problem looks additive or multiplicative. This the seasonal decompose function returns a result object. The result object contains the arrays to access 4 pieces of important data from the decomposition. And okay, so with that, let's do that, and we will then get to see the result object. So actually, the result object provides us access to the trend and seasonal series as arrays. It also provides access to the residuals, which are the time series after the trend and seasonal component are removed. And finally, the original or observed data is also stored. So to use the first, let me see if I'm getting BTC price daily dot weighted price, if I'm getting this as an array. Yeah, so yeah, this is my weighted price. Length is 3379, d type float 64. Okay, and here again, remember this length we got 3379. That's because it's a daily price. We resampled our original data to daily 24-hour basis with this code right here. That is, it actually grouped by the weighted price column for 24 hours together. Otherwise, as you remember, our original data was actually into millions because they provided on each minute Bitcoin prices. So this was the original shape, 4,857,377. But we compressed that on a daily basis. That's how I got my final data frame, only 3379 columns. Yeah, so now let's apply the seasonal decompose. Oops, sorry. Fixed size will be a tuple. Seasonal decompose. It will take my series as the first argument. X is array like, which is a time series. If 2D individual series are in columns, X must contain 2 complete cycles. Model is additive or multiplicative, optional. This is an optional parameter. Type of seasonal component. And let me see, period. Extrapolate trained. Okay, all these are optional. But I am going to give the model and the period as well. First series model in this case is additive, and period is equal to 1. Result.plot. Data frame object has no attribute called figure. Why is that? Let me see. So it was coming because this PLT variable was defined to be something else, and that variable was still there in the memory. So I just had to restart the notebook. And so after running this cell, this is the output that I am getting. And so this is a result of seasonal decompose. And look at this image more importantly. So I have a trend plot, I have a seasonal, and I have residual plot. And looking at this time series, that is the decomposition of the time series, so we don't really observe any seasonality. Also, there is no looking at these two plots, there is no constant mean or variance or covariance. Hence, this looks like to be non-stationary, but I will perform a statistical test like Kpss and ADF to confirm my understanding. But first, let's plot ACF and PACF graph. So the ACF stands for autocorrelation function, and PACF stands for partial autocorrelation function. The ACF and PACF are used to figure out the order of ARMA and ARMA model. That is, AR stands for autoregressive, MA stands for moving average, and ARMA models means autoregressive moving average models. And autocorrelation here is the correlation between a time series with a lagged version of itself. The ACF starts at a lag of 0, which is a correlation of the time series with itself, and therefore results in a correlation of 1. And then progressively we measure the correlation with different lags, that is, with increasing lags. So ACF, we have already imported this. It takes a series, lags equal to 50, set at 0.05. Also, it takes a size. Okay, this is my ACF for weighted price. So, simply stated, ACF explains how the present value of a given time series is correlated with the past. And the past means maybe it may be 1 unit past, 2 unit past, 3 unit past, and like this, n unit past values. In the ACF plot, the y-axis expresses the correlation coefficient, where whereas the x-axis mentions the number of lags, and thereby these values on the vertical axis, they are the correlation coefficients, and on the horizontal axis I have the number of lags, and I have a maximum of 50 lags because here I have put as a parameter lags equal to 50. A time series can have components like trends, seasonality, cyclic, and residual. ACF considers all of these components while finding the correlations, hence it's a complete auto-correlation plot. And here in this case, we see the effect barely deteriorates over time. So past values affect the present values. That means the more lags we include, the better our model will fit the dataset. But now the risk is coefficients might predict the dataset too well, causing an overfitting. So in this case, the strategy is to only include only those lags which have a direct effect on our present value. Hence, next I'm going to plot the PSAF, that is partial ACF. It's actually just similar, so I can just copy this one. Only changed here, plot PSAF. Oops. Plot PSAF, lags and alpha remains same, lags 50, and I am going to use another parameter here, which is method equal to OLS. And this will become PSCF. Let's increase the size to 20. 25 actually, because it is going to be a long horizontal log plot. Yeah, so this is the PSCF plot, and what we see is that the coefficients, that is these values are the coefficients. So coefficients values beyond lag of more than 5 are statistically not significant, and their impact on the model is minimum, except a few spikes maybe at around here at 8 or so, maybe around here, which is at around 10 or 11, at 22 right here. But beyond these small spikes at around these points, more than lag 5 is not really statistically that significant. So next I am going to check the all important stationarity of my time series. And for that, I'm going to use two very well-known technique for stationarity checking, which is Kpss test and the Adf test. We already have imported the Kpss method module at the very top that takes a series and CT. And what it outputs are four things. First is stats. You definitely should check the documentation. Then P, lags, and critical values. Critical values. Okay, let's run this. Okay, now what I'm going to do, I'm going to just print these stats P and critical values one by one. Okay, that's output. So p value 0.01, test statistics 0.6463, and these are my critical values. Now p value is less than, if p value is only 0.01, that means this time series is not stationary, because here the null hypothesis is that the time series is stationary. That means if the p-value is less than the significant level, which is 0.05, then we reject the null hypothesis and conclude that the series is not stationary, and vice versa. So you can actually include that in a little code like this. If p is less than 0.05, series is not stationary, otherwise series is stationary. So in this case, it is not stationary. Now, a little bit of interpretation of these Kpss test results. So what you got from Kpss are these four things: stats, P, lags, critical values. So the first one is the Kpss statistics, then the p-value, then number of lags used by the test, and lastly the critical values. So here the p-value reported by the test is a probability score based on which you can decide whether to reject the null hypothesis or not. If the p-value is less than a predefined alpha label, typically 0.05, we reject the null hypothesis. Then this Kpss statistic is the actual test statistic that is computed while performing the test. For our case, we got this as this value 0.6463. And then the number of lags reported is a number of lags of the series that was actually used by the model equation of the Kpss test. And finally, in order to reject the null hypothesis, the test statistic should be greater than the provided critical value. And if it is in fact higher than the target critical value, then that should automatically reflect in a low p value. That is, if the p value is less than 0.05, the Kpss statistic will be greater than the 5% critical value, which is exactly what we got here. P-value is less than 0.05 and we got the test statistics is more than 5%. And now I'm going to do the other test for stationarity, which is Adf test. And this is actually this is actually more popular than sometimes, not always, more popular than the Kpss test. So in the Adf test, the only difference here is the null hypothesis, which is just the opposite of Kpss. The null hypothesis of the test here is the presence of unit root. That is, the series is non-stationary. And I'm going to just write a little util function for this Adf test time. Okay, no, let's first get my result. Df test result is add cooler actually let's do one thing. My df test print, because whatever these returns, based on that I am going to write my function, because based on the output structure. So here this will be series, because our time series has been named as series. Auto lag AIC, run this. Okay, so this is what I get from my Adf test. So basically this first value is the test statistics here from the Adf test. This is p value, this is lags used, and the number of observation used, 3349. And these are all my critical values. So yeah, so now what I'm going to do in my, I wanted this structure to actually see, because my next function will refer to this data structure, that is the structure of the data in the output. So pd.series, I'm going to take the first 4 values, 0 to 4, and then create the index, which will be this. Index equal to test statistics, p-value, lags, number of lags used, number of observation used. Okay. Now for the last part, that is for all these critical values, let's do this for df output I'm going to do a percentage yes, then percentage key, print df output. And here again, the same logic about the p-values, which is if p-value is more than 0.05, then series is not stationary. Otherwise, series is stationary. Okay, with that, I'm just going to execute this function. Pandas has no attribute series. 1 second. This is a capital S. Critical value. Let me fix this. Yeah. So now this function, this is output I got, test statistic 6.30, p-value 0.01. Finally, the conclusion from this function is this one, that the series is stationary. So the important thing to note here is that from the ADF test, I got a series is stationary, but from the Kpss test, I got series is not stationary. So the key conclusion or the next step that we have to do when we get a contradictory result from Kpss and ADF test for the p-value is that it means that the series is difference stationary, and in this case we need to use differencing to make the series stationary. But this video I'm not doing the differencing yet because that will be a topic of a separate video. I just here in this case I just wanted to go ahead with the model building to forecast the price. And so yeah, so right now I'm moving on to do the feature engineering so that I can implement my profit, Lstm and ARIMA model. Yeah, so the next step is feature engineering. So here I am going to make use of rolling windows. So basically, I'm going to create 6 new features with rolling windows and append them to the original data frame. And the reason is that time series can be very noisy due to high fluctuation in the market. As a result, it becomes difficult to gauge a trend or pattern in the data, especially a highly volatile market like BTC market. So here we are, when we are looking at the daily data, there's quite a bit of noise present. It would be nice if we could average these out by a week, that is 7 days, which is where the rolling window or the rolling mean comes in. So a rolling mean or moving average is a transformation method which helps average out noise from data. It works by simply splitting and aggregating the data into windows according to functions such as mean, median, count, etc. For this example, we will use a rolling mean for 3 days, 7 days, and 30 days. So first, df equal to and my rolling features are, I'm going to just define a list with open, high, low, close and volume BTC. They are my rolling features. Windows will be Windows, first one will be 3, second one 7, last one 30. So first convert our original DF to a rolling DF of 3 day, 7 day and 30 days. So df I'm making use of this rolling method, which takes a window parameter, which in my case will be window. Oh, I forgot to name them. So the first window is window 1, then window 2, window 3. Really, no need of this S. So my first window is window 1. Yeah. And I need to change the same thing with window equal to 2 and window equal to 3. This will be my 7-day and this will be my 30-day. So now that I have got my rolled features for the rolling window of 3 days, 7-day, and 30-day, the new 6 new features will be 3 for the mean and 3 for standard deviation. So what I mean is that will be df day dot mean shifted with 1 and then reset index. Okay, so that's what I mean. And this shift function, what they do in pandas is that the shift this shifts the index by desired number of periods. It takes a scalar parameter called the period, that is this one here, which represent the number of shifts to be made over the desired axis. The desired axis is by default it's 1, and sorry, this scalar number by default is 1 and the desired axis by default is 0. So it will shift by 1 row over here. That means it is shifting values vertically along the axis 0, that is along the rows, by one number, that is 1 row. And I need for this 3-day, I also need for 7-day and 30 days, like this. And then that's a mean, and I also need the same for my standard deviation, and that's this. Exactly the same code here, only thing I'm changing is instead of dot mean I'm using dot std to get the standard deviation. So these are my 6 new features, and if you want to check out any one of them, just print it. Oh, I did not run on this cells. Run. Yeah, so df std 30-day, that will look like this. And note that I'm saying 2 rows of nan values, and that's because I have applied the shift method twice. So when the way that shift works is that when it shifts a number of rows along the vertical axis, nan will be filled for the missing values introduced as a result of the shifting. And here, because on the same dataset I applied the shift twice, I got 2 rows of nan values. And now the next step is to create 6 new features and append them to the original data frame. So I need to run a loop here. Feature. My original dataset, the data frame is named as df, and that's what I am going to change. And the way that I'm going to change, I'm going to create a new column which will be named as, let's name it feature. To that, I will be, for the first 3 set, which is a mean lag, I am appending the word mean lag. Then window window 1. Yeah, looks good. And that will be my df mean 3D feature. So all it will do is, so for example, these df mean, say for example, the 3D I'm printing. So this is the whole df mean 3D. From there, I am, for the first one, let's say the open price, I'm just taking with this line, a df mean 3D feature. It will loop through all the rolling features. So that means the first one will be the open price. And that will take the open price from this mean df and append it to my original df. And so I have to do it for all the rest of the 5 features. So let's do that. Yeah, cool. And finally, after the loop, I need to do the imputation again for the nan values. df mean and df dot. Cool. This is my new data frame with 6 new features added, and which are all these. So this is my feature engineering. Pretty important when you are doing some model with large amounts of data, especially when you're feeding them to a deep neural network, which is what I'm going to do here with Lstm model. So all these features are the new ones that we just created. Okay. And the key benefit of doing this moving average is that using this rolling mean will create a lot less noise, or rather remove the noisy part from the dataset, and it will be more effective to detect trend from the data. And now let's extract time and date features from the date column. That is, we have these where is it? Okay, actually I'm going to extract the time and date from the timestamp, and for that I need just that datetime module. So df, because all these are features, month, week, day, or day of week, all these are important parts of trading strategy, etc. And some trends or some important intelligence could be extracted from these features. Very important for time series based asset pricing project. df month will be, and similarly I need to do for week, for day, and also day of week. Yeah, and let's print df again. Here now I will see 4 more features, which are month, week, day, and day of the week. Cool. So okay, with that, my feature engineering is kind of done, and I am going to do the model building here. But obviously remember that there are many more features that you can create for even more exhaustive calculation, or even more exhaustive feature engineering. For example, you can combine 2 features, you can take differences of 2 features, and there are many more ideas indeed, and there are quite a few research papers on BTC, Bitcoin price prediction, and feature engineering, best optimal feature engineering to include. You can even take prices from other asset prices, which are, that is, other cryptocurrency prices, to do your feature engineering. And now finally the model building part. First I'm going to implement ARIMA, then Facebook Profit, and then finally Lstm, and compare their performance on the validation dataset. So to measure the performance of our forecasting model, we typically want to split the time series into a training period and a validation period. This is called fixed partitioning. If the time series has some seasonality, you generally want to ensure that each period contains a whole number of seasons. For example, 1 year or 2 year or 3 years. If the time series has yearly seasonality, you generally don't want to have only 1 year and a half, or else some months will be represented more than others. Then also we will train our model on the training period. We will evaluate it on the validation period. Here's where you can experiment to find the right architecture for training and work on it and your hyperparameters, etc., until you get the desired performance measured using the validation set. Often once you have done that, you can retrain using both the training and validation data and then test on the test period to see if your model will perform just as well. And if it does indeed, that is, if your model really performs well, then you could take the unusual step of retraining again using also the test data. But why would you do that? Well, it's because the test data is the closest data you have to the current point in time. And as such, it's often the strongest signal in determining future values. If your model is not trained using that data too, then it may not be optimal. Here we will opt for a holdout based validation. Holdout is used very frequently with time series data. In this case, we will select all the data for 2020 as holdout and train our model on all the data from 2012 to 2019. So the splitting point is lesser equal to 2020 and more or equal to 2020. So let's define those variables. All right, I have 2923 number of rows in my train and 456 in the valid. Okay, the first model I'm going to do is ARIMA. Now, ARIMA is an acronym for Autoregressive Integrated Moving Average. It is a class of model that captures a suite of different standard temporal structures in time series data. This acronym is descriptive of its actual job. And what are the actual jobs? Briefly, they are about three things, which are, let me put it here. First one is auto regression, AR, a model that uses the dependent relationship between an observation and some number of lagged observations. And then the integrated, which is about the use of differencing of raw observation, for example, subtracting an observation from an observation at the previous time stamp in order to make the time series stationary. And lastly, moving average, a model that uses dependency between an observation and a residual error from a moving average model applied to lagged observation. And the standard notation is used for ARIMA, which is ARIMA PDQ. So which are the PDQ? They are these things. So here normally it is represented in this form. So the P represent the number of lagged observation included in the model, also called the lag order. It's a pattern of growth decline in the data which is accounted for here. And then D is about the number of times that the raw observations are differenced, also called the degree of differencing. That is the rate of change of growth or decline is accounted for here. And lastly, the Q is about the size of the moving average window, also called the order of moving average. So with this, the noise between time points is accounted for. Yeah, so now the actual code to do the ARIMA model. So I'm going to import PM. I'm going to use PMDARIMA as PM. So like I discussed at the very first part of the video, you have to install this package. And now I am going to define an exogenous variables, that is all the engineered features, not exogenous variable, it's actually exogenous features. So these are all the features that we developed in the previous steps. So these are they. So you can see open mean lag 3, open mean lag 7, similarly. So all these features we already defined here. And what I'm excluding from here, I'm excluding the original features, that is original open, high, low, close, volume, data, etc. And obviously I'm also not including the timestamp here. And the weighted price is a Y value, that is a target value, that also not included in the exogenous features. And now the training for the model. So pm.auto ARIMA, it takes the Y value as a first argument, which in this case is df trend dot weighted price. US exogenous is my df trend equal to ignore suppress warning, also true. Sorry, exogenous equal to first number of periods, PERIODS, because now I'm forecasting, so I need to use the forecasted value from my df valid part of the dataset. And lastly, so this is a new forecasted price of the Bitcoin for as a result of the model training. That's what I'm creating. This is a new column which will have the forecasted price from the trained model. Cool. And after running this model, I'm just going to plot these weighted price versus that is actual price and the forecast ARIMAX on from the df valid, and this is the output. The blue line for weighted price and the forecast for ARIMAX. And now some evaluation metrics here. So I'm importing mean squared error and mean absolute error that I'm going to use again and again for both ARIMAX, FB Profit, and also Lstm. So what I'm going to do, print RMAC, that would be mean squared error. To that, I need to pass the actual price and a forecast price. So DA price what is that? Forecast ARIMAX. Yeah, and similarly, I need to do for the mean absolute error, MAE ARIMAX. Okay, so when I run these cells, I get the output as RMSE is 18,100 and mean absolute error is 10,733. Not too bad, but not too good as well. Okay, next I am going to plot the model diagnostics. So I have a function for that, model dot plot diagnostics. And the output of that is this particular plot. So I have here the histogram plus estimated density and standard residuals, histogram plus estimated density. Yeah, so that's the output from my model diagnostics. And now the next model is FB Profit. Okay. Oh, sorry. This will go here. Okay. And the first thing is to import profit from FB Profit, import profit. Yeah. Now, I'm going to be resampling the original data to day label and forward fill the missing values. So daily data. I think I have done it previously, but I'm just creating a new variable doing it. Still missing, that's our method. Daily data. Okay, next what I need to do is renaming the columns according to the profit's requirement. Now, before we go ahead with the profit, a quick word on how profit works. So here I'm looking at Geek for Geeks pages, time series analysis using FB Profit. So profit is a procedure for forecasting time series data based on an additive model where nonlinear trends are fit with yearly, weekly, and daily seasonality plus holiday effects. It works best with time series that have strong seasonal effects and several seasons of historical data. Profit is robust to missing data and shifts in the trends and typically handles outliers pretty well. And about the equation of profit, so the general idea of the model is similar to a generalized additive model. The profit equation fits trend, seasonality, and holiday. And this is the equation of profit: yt equal to gt plus st plus ht plus the error term. So gt refers to trend, st refers to seasonality, ht refers to effects of the holidays, et refers to the unconditional changes that is specific to a business or a person or a circumstance. It's also called the error term. Yt is a forecast. And yeah, so profit is a pretty robust model. You definitely should be using it. Now going back to my Yeah, the next step is we already have resampled. So for profit, I need to have um, two columns named as DS and Y. You can check out their official documentation. So that's what I'm going to be creating here. Daily data FP equal to my first is time stamp. These are the existing column names, which I'm renaming to time DS and the weighted price. That will be renamed as Y. Data FB dot. And when I do that, this is how the data will look like. So I have two columns here, DS and Y. DS is a timestamp, Y is the weighted price. And that's these are pretty well mentioned in the official documentation of Profit. So here I'm looking at the Profit Quick Start Guide. And what they're saying is the input to Profit is always a data frame with two columns, DS and Y. The DS, that is data stamp. DS actually represent the data stamp or the date stamp or the timestamp. So DS column should be of a format expected by pandas, ideally YYYYMMDD for a date. The Y column must be numeric and represents a measurement we wish to forecast. All right. And here as well, I need a split date, which will be this 2020-0101. And based on these, I'm going to create my trend set and the valid set. Date stamp should be less equal to split date, and my test split should be DS greater than split date. Yeah. And split. Okay, and if I check their shape, this is the shape they are. So the train date shape is 2924 by 2 and test date shape is 455 by 2. And just so you understand that the way that I split this particular variable, this will create a Boolean list, and then that Boolean list will be applied on this data frame, daily data FB. So why Boolean? Because this train split will check the DS column and check whether a particular value of the DS column is less or equal to split date. If this condition is satisfied, then that will be a true value. Otherwise, it is zero value or false value. So let's actually print this trend split, and then it will make sense. So if I print, yeah. So that's how trend split is the output. It looks like this: true, true, true for all the initial dates, and then for all the ending dates, that is which is after that particular date, all false. And then when this Boolean list is applied on my data frame, then accordingly only those parts of the data frame will be captured or will be extracted with this variable train FB. And rest part of the data set where this trend split is equal to false, that will be captured by the test split, and that's a test FB. Okay, so that was about it. Now I need to actually execute the profit model. Create an instance of the profit object, and then for feature and XO model FB. Oh, that should be, I wanted to name it as FB profit. Yeah. DF trend. I also need to add all the exogenous features. And then finally rename it. For renaming, I can just copy paste this part. Similarly, I need to do for syntactical error. Where is that? Yeah. I also need to do for df valid, which will actually be my forecast. Model profit dot and fit will be replaced with predict. Otherwise, everything remains same. And when I run this, I get this data set. And here it is the forecast part of the data set, and all these numbers are from these on the valid part of the data set. So this is a valuation part of the model, and weighted price here is represented by this y hat variable. So we can see this data frame has these new columns, which are y hat lower, y hat upper, and this y hat. So y hat is a predicted forecast, and y hat lower and upper is just the lower bound and the upper bound of the forecast. And just one more quick point on these add regressor. So additional regressors can be added to the linear part of the model using these add regressor model method here. All right, now what's next? So next I'm going to plot the forecast from the FB profit model. And the plotting is super easy here with FB profit. You just pass this. I'm also going to plot the model. The plot. Next, I'm going to use plot components so that I can see the different components of the forecast. Model dot. Sorry, plot components. Yes. So the output of this is when with the forecast only, that is just the model profit dot model FB profit dot plot. I'm getting this plot, Here, the black line is actual data points in our data set, and the deep blue line is the predicted or the forecast values. And then for the model.plot components, I'm getting this 4 or 5 different components. And here, these light blue lines shows me the boundaries. And this is the trend, this is weekly, then yearly. Yeah, so it gives a lot of visualization. And the important thing that I want to plot from a B profit is the comparison between weighted price and the forecasted profit price. So DF our new column name was forecast profit, right? Let me quickly check. Yeah, with this line, I have already created this new column names, which has all the values from Y hat, which is predicted profit price. That means I can do this now. $18.9. And when I run this cell, I get this plot right here. So we can see this orange line is the forecast values, and they are almost going head to head with the actual weighted price values. And finally, what do I need to have? Just like in ARIMA, we need to get the RMSE and the MAE values for my FB profit forecast. And this is the code. So test MAE between the weighted price and the forecast profit, and also test RMSE. And the values that we are getting here are really much better. So the test MAE 690 and the profits test RMSE is 1308. Remember, this is way better than the ARIMA model. All right, with that, FB profit is over. My next model is Xgboost, the good old Xgboost. For this, I need to import all the libraries and also need to define the variable for xtrain and xtest, and also ytrain, ytest. Exogenous features. What price? And similarly, my x test and y test will be the valid exogenous features and the valid weighted price. Cool. And then just define my the instance of xgb regressor, which is xgb.xgb regressor, and define the hyperparameters. These are my hyperparameters. And what else? I need to now define the model. And that's my model, randomized search CB. The reg, this one is coming from this one, this line. That is, this is an instance of XGB regressor. That's the model I'm using. Otherwise, param distribution is just this. Let me zoom out a little bit. Param distribution is just this params in iteration in jobs -1. So it will take as many CPUs as available. CV equal to 5, verbose 3. Okay. With that, I can just do model.fit, and that will start the training. And then to get the best params, I just need to print model.bestscore and model.bestestimator.getParams. That will output me, wait a second, this one. model based score. Oh, 1 second. Model based score and model based params. Don't worry, the entire notebook will be available in my GitHub, that link of which I'll give in the description. So all these codes will be easily available. Okay, and now the next line is model.best estimator, and that's XGB regressor. That's the output of model.best estimator. And then the actual prediction. I'm creating a new column named as predicted. And this is under the Xgboost model, remember. Model.predict. To this, I pass X train. Similarly, I need model train. Actually, I'm just going to plot now. So just, yeah. Price, and also compare this with this. Plot, just like we did for AB profit. Plot big size. Let's do 18.9. And that gives me this plot. We can see again the predicted weighted price and the weighted price in blue. Next, I'm going to do for the DF valid portion. DF valid forecast X test. And now let's concatenate them. DF train and DF valid. Okay, and now I'm going to plot. So I just can use this line, just change DF trend to overall data. Yeah, that should do. And the result of that is this plot. So here the difference is that I can see the sorry, I can see the entire real values for the entire span of time starting from 2012, and my predicted value is in orange, which is for the valid or the test portion of the data. And just to compare, I also plotted this next plot here, which is the plot between weighted price and forecast Xgboost, but now it's only for the DF valid portion of the data. That is only for the test portion of the data. So I will have the blue and the orange line for the entire period. And as we remember, the valid test data, that is validation data, started from 1 January 2020. So that's what we are seeing here. Okay. And now time to calculate the mean absolute error and also the RMAC for the Xgboost as well. Let's do that. So this is the code for the train portion of the data. So I am calculating train MAE, then train RMAC, and the train R square. Okay, I did not import R square, so I need to import that from sklearn. Yeah. And this is a train portion. I need to do the same for my test data as well. And this is for the test data. Remember, to each of these function, I'm just passing the true value and the predicted value for the target variable. And what is my target variable? The valid weighted price. That's my target variable, and this is a predicted of the same variable. So that's exact two things I am passing to each one of them here as well. Okay, let's see the output. Cool. This is my output for Xgboost model. So RMAC 210 for the train portion, and for the test, the RMAC is 13626. All right, it is better than ARIMA, but worse than FB Profit. So yeah, that's a score from my, that's overall performance score or evaluation metric from my Xgboost model. Next, okay, now before going further, before going to LSTM, I need to be comparing the models. So I will plot few things, comparing the actual ARIMAX, Profit, and Xgboost. And for that, all I need to be doing is just to capture the relevant column names. We have already defined all the column names. So I am just going to capture the column names for the real data, that is weighted price, and then all the forecast. And this is my code. So all I'm doing, df valid weighted price, this is the real actual value. Then I'm also capturing forecast ARIMAX, forecast profit, forecast Xgboost, and then plotting them. So this is the final plot. Here, the weighted price is a blue line, and these are the other color coding here: forecast ARIMAX, forecast profit, and forecast Xgboost. Okay, so looks like these Profit and ARIMAX, so the Profit is really performing really well among all the three. Even Xgboost, the prediction is not tracking the real data. So Profit till now is the best performer. And to check that, I just printed the actual number for all the three models, that is ARIMAX, FB Profit, and Xgboost. And this is the result. So all I'm doing here, let's check out the code. All I'm doing for the first three lines is for the RMAC, mean squared error. I'm taking a square root of them. And what I'm passing, the same two things: weighted price and forecast ARIMAX, weighted price, forecast profit, weighted price, forecast Xgboost. So this is my RMAC, and then the next one is MAE. And MAE as well, I'm passing weighted price and forecast for all the three models, and this is the result. And look at the result. ARIMAX RMAC is 18,100, FB Profit only 1,308, Xgboost RMAC is 13,626. Similarly, for the MAE, ARIMAX is the worst MAE, Xgboost is the second best, and FB Profit is way better, 690. Yeah, so FB Profit is outperforming the other models by a large margin. So now finally, the final model of this exercise, which is LSTM. And the first step for LSTM is defining a price series for all the weighted price in my data frame. Price dot yeah, this price will be a series. Let's check the the shape. Yeah, 3379 is the total number of rows, just as it were. Okay, now what I'm going to check previously, what was the shape of our trend? That is all the previous model, Xgboost, FB Profit, etc. What was the trend size we created? So the variable was df trend. I'm just going to create a shape. Yeah, 2923 was the number of total train data points. So for LSTM as well, while I'm splitting the data for train and test, I need to split in this way. That is 2923 will be my train set, will be number of train counts, and the rest will be test. So let's just split the data manually. Train data. series 2923 till the rest. Yeah. And now I need to do the transformation. Remember here a very important part that is applicable almost any data science machine learning project, that to avoid data leakage, you always split your data to train and test before applying the transformation. And what is a transformation? Like min max scaling or normalization, etc. So here as well, I first split the data and only then I'm going to do min max scaling on my data. And that means the specifically what it means is that from the min max scaler, I'm going to apply the fit transform method on only the trained data. And on the test data, I'm only going to apply the transform method, not the fit transform. Thereby, what's happening underlying is that no characteristic of the test data set is leaking into my model training. That is, if I apply fit transform on the test data, that will mean the standard deviation and mean and those data's main attributes are getting known to my model training. But that's not what I want, because that will create problems. That will create a highly overfitted model. So that's the main workflow here, that you train and you split the data set, then you apply the transformation on the data set, that is the scaling the data set, and that during the scaling you apply fit transform only on the trained data and apply transform only on the test data. So first import min max scaler. Range equal to 0 and 1. Sorry. So this is what I am talking about, that this is my trained data and I'm just directly going to apply fit transform. To that I cross train data reshape -1, that will be inferred the first dimension and the next dimension is 1. Now, very importantly, for the scaled test data, I'm no more going to apply fit transform, but only transform. Cool. And now if I just run the cell and also train data dot. Yeah, so the 2923 is the number of total rows under my train set, and that's exactly what was there for the df train.shape. That is earlier model of Bprofit Xgboost were trained on 2923 number of train data portions. Okay, now the next thing for my LSTM, I need to define a windowing function, because as we know that LSTM takes a window, it's a sliding window kind of mechanism. So during the training, I have to feed the model only a single window data one after another. So let's define a model which will return me a window of data set. So here basically for each window, all data up to the last but one data point will be appended to a x variable, and the last data point of a single window will be the y variable. So I will define two empty lists, data x and data y. Y is a target variable, of course. For I in range, res minus time step minus 1. This is the range over which I'm looping. And first, let's extract the x variable, that is a feature variables part of the current window series, starting from I, going up to I plus time step. Sorry, time step. So this is the first dimension, and the next dimension is 0. And that I need to append to data x dot a. Okay, now I also need to get the target variable, that is y variable, which will be appended to my data y. So that I can do in a, let's called a b, and that will be series I step 0. So this b is just this value. So note that a started with a slice notation. I took a range of values, but for y I'm taking the single value for the first dimension, and then the 0 for the next dimension, and that b need to be appended to data y dot append b. Yeah, and the return from the function will be, it was just a list, Python list, so I'm converting it to a NumPy array, data x, and also np dot array data y. Yeah, that completes this method. And now I need to execute this method, this util function, to get my these two data x and data y array from the whole train dataset and the test dataset. So what I'm going to do, get window method. To that I pass the first argument, train data, which we already have defined, and the time step is actually the look back period. Time step for this is equal to 100, and that will return me x train and y train. Similarly, I need to do for x test and y test, and here that will be my test data. Yeah, you can check the shape by printing this. Oh, I did not run this cell. Yeah, so that's my final structure of the data that will be passed to the Lstm model. So xtrain shape, ytrain shape, xtest shape, ytest shape, and in both I have 2822 as train and xtest 355 number of data set. And for the feature, obviously the second dimension is 100 because that's my look back period. And now an important part, which is to reshape the inputs to be number of samples by time steps by features. So let's do that. Because that's a requirement of the Lstm model. So here I have to reshape it to number of samples, num samples, time steps, and features. Okay, so x train So our earlier X train was 2822 by 100. And what I need is, I need 2822 by 100 by 1. Here 1 represent the features. And 100 is time steps or the look back period. So shape 0. Then, yeah, actually, I can do the same thing 1 and 1. Similarly, for X test, okay, yeah, that should do. And now I just need to print, and let's see, cool. And my Y train and Y test remains the same. I'm just checking it again. Yeah, these are just a single dimensional vector actually, because they are just the target values, Y value. So it's a single vertical vector. So they looks good. Okay, so now I'm fully ready to start my LSTM model, but first all the imports, and then my actually building the LSTM network. Is it importing out correctly? Yeah. Okay, so first I'm using sequential module of Keras. So adding my first LSTM layer here and some dropout also for regularization. So regressor TM. The first one, the first argument is units, which is the shape of the output dimension. Units, I'm keeping it at 50. Return sequence true. Input shape will be equal to X train 1 and 1. Okay, that's the first layer, and also I need to add the dropout. Dropout is 0.2. 20% of the nodes will be dropped. Now adding a second LSTM layer and also dropout. Let's just copy this thing. Do I need to change anything? Return sequence true, input shape, I don't need that. Dropout remains the same. Again, I'm copying this to add a third LSTM layer, and that looks good. And then also I'm adding a fourth LSTM layer, and here I also don't need the return sequence true because there is no more LSTM. So I don't need a compatibility of dimensions here, because the next one is going to be my dense layer. Okay, so adding the output layer here, that would be dense units equal to 1. That is a fully connected dense layer, hence units equal to 1. Finally, compile the model. Optimizer is Atom. Loss is mean squared error. AD. Okay, and let's run it. Clear cell outputs, and I need to create a model summary. I need to print the model summary. Yeah. That is my model summary. So we can see we have LSTM, then the next LSTM, third LSTM, fourth LSTM. I also have all the dropout layers and finally the dense layer. Okay, all looks good. So I am all ready to run my long LSTM model, and it may take 10 to 15 minutes. So history variable is output. What I'm going to do, shuffle is true. Oh, sorry, shuffle. I want to keep it false. Yeah. Okay. And immediately after the training, I've not yet started the training, but I am keeping the code ready for plotting the result. Because here I'm going to plot the train loss and validation loss versus the epochs. So plt dot 16.7. So all the output result will be available in the history variable, so I can get hold of. You can just print the history variable after the training, and you will get all the parameters that is available within this variable. So I know history dot history. From that, I need to take loss. Train loss. I also need to do validation loss. Then that's it, pretty much. Okay. And after like 15 minutes, all my training was over for 50 epochs. And the final loss was 0.0014, val loss was 0.0019. And the plot output I got is this. So we can see that the validation loss was really high at the initial part of the epochs, but then it started reducing and intermittently it went up, but towards the end of 50 it was at this point. Now that the model is trained and all, I need to do the predictions and also create ultimately the RMSE and the MAE, just like we did for other models. So first the prediction and checking the performance. Train, predict. It's very easy now because I have the regressor variable which is fully trained, so I can just do predict. Do that, I pass my x train. Similarly, I do for test. And before calculating the performance metrics, I need to do a reverse transformation because we scale the data set with the min-max scaler. But with so all the data is between a particular small values now, between the min and max and scaled. But with that, I cannot calculate my metrics because the metrics also will be super small. So I need to get back the original form of the data set. So that's called inverse transform. So what I'm going to do, y train in. Actually, this inverse transform method that they have in sklearn is super handy. For the test as well. And I also need to do the same for my train predict. Predict.inv. Because these train and test predict values as well, their numerical values are as well are scaled, because the whole data set xtrain and xtest was scaled. So sorry, this is in yeah. Okay. And lastly, the plotting. So I need to flatten it. Next will be train predict inverse. And this is predicted price. Cool. And when I ran this plot, this is what I get. Sorry, not this. 1 second. Yeah, this is the plot that I get. So this is the final output from my Lstm model. And the red one is for predictions and blue one is for the actual values. So it's looking pretty good actually, not too bad. But still looks like, just by looking at the plot, looks like FB Profit is still the winner. But let's see, we will figure out that in a second when we calculate the RMSE and MAE. But that plot was for the train and predicted. I also need to do the same plot for my test actual and test predicted. So I can copy and paste the same code here and change this y train inverse to y test inverse, and this also test predict actual, and yeah, the rest of the things remains the same. And the output of that is this one. And obviously, as we expected here, the predicted red line is not tracking the original blue line as close, because it's a test data set, it's a validation data set. And so here, that's what I'm saying. That's what I was saying, that the Lstm model looks like lagging behind FB Profit, because for FB Profit, even for the validation data set, the predicted line, this red line, was almost tracking very close to the actual price data set. And that's why we are at the final step of calculating the RMSE and MAE for the Lstm. Calculating RMSE and MAE properly after inversing the transformation. So we are already done with the inverse transformation. So now we can just pass those y train inverse and y test inverse to the method mean squared error and mean absolute error. So train RMSE verse will be why this is mean y train inverse and train predict inverse. Similarly for test RMSE would be mean squared error y. Okay, and we have to do the same for calculating the MAE. Let's mean absolute error. Take out the square root part because it's an MAE. And y train, the rest of the things looks to be good. Yeah. So what I do, print test RMSE inverse. Yeah. And this is the result that I get from my Lstm RMSE of 1016 for the train, and RMSE for the test is 10,222. So it is better than ARIMAX, kind of equivalent with Xgboost, but way far, that is way worse than my FB profit prediction, FB profit evaluation metrics. So we see that for this particular data set and for this modeling exercise, FB profit really outperformed the rest of the models. So these were the result from my previous model. So ARIMAX 18,100 RMSE, FB profit 1308, Xgboost 13626, and compare that with the Lstm. What did I get? For Lstm, I got RMSE of 101x for the train, but for the test, that is actual the one that matters, 10,222, which is better than ARIMAX, even better than Xgboost, but not even close to FB profit. And even on the MAE part, mean absolute error, ARIMAX was 10,733. And what did I get? 5767. So much better than ARIMAX. But compare that with the FB profit only 690. And so its FB profit is really the best performer in this exercise. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.